Assalamualaikum wabarakatuh and good evening to everyone. So today's we're going to start our lecture number 2, symmetric encryption and message confidentiality. So this is the outline. First, basic cryptography, and then the principle of private key or symmetric encryption, then the algorithm of symmetric encryption, whether it's stream cipher or block cipher, then cipher block modes of operation, the stream ciphers, and also a key distribution. So, a cryptography. Nowadays, if you talk about cryptographies, it's being hijacked. It, it's already being hijacked by the cryptocurrency. Okay, when you mention crypto, people think that it's a Bitcoin or Ethereum. It's a cryptocurrency. No, the crypto is actually the words is a short form of cryptography, which means hidden. Okay, hidden. Cryptography refers to the study of mathematical techniques to achieve secure communication. I mean, this last time when during the Romans era, maybe earlier than that, how does we conceive or we hidden the message so that our enemy cannot read it. Okay, it's very important. Last times in ancient world, of course, in the modern world as well. It is very important to protect data in transit, meaning that when you submit in transmission, when you submit or you transmit the data from source to the destination during the transmission. Okay, so this is source, so this is destination. During the transmission here, this part, communication channels like protocols are insecure. This is internet. Okay, this is internet. It's very important to protect data in transit. Okay, cryptography is a major technique behind information and network security and means to achieve first the authentication, the data integrity, the confidentiality, digital signature, and of course the privacy. So you learn about CIA, confidentiality, integrity, and authentication. Now we have a digital signature and of course a privacy. So cryptography techniques. So the first one, cryptography techniques. There are a number of cryptography techniques, but we can differentiate it into two main techniques. One is symmetric encryption, and another one is asymmetric encryption. And of course, we have also a hash function to make it more secure and to scramble our messages or our password, even our password. It can also be used to protect data in file storage. Okay, hash function is actually in password encryption. They usually use a hash function for password. Okay, for password. Usually, when you want to log in into the system, let's say it is your, I don't know, maybe your email, uh, Hotmail, or no, maybe some like insecure system. Maybe it's like your anime account or something. If like you forgot your password, when you try to retrieve the password, they give you a new password, new temporary password, meaning that your password is stored in the plain text. Okay, the password is stored in the plain text, which we will learn after this was the plain text, which means it's not secure. Okay, your password is stored in a plain text, so it means that that data or that system is not secure. Other than files or message, it also can be used to protect data in file storage. Any data, you can encrypt that as well. So this is the other names of symmetric encryption: shared secret key encryption, because you have to share the key; single key encryption, one key for all; secret key encryption, you must keep it secret; one key encryption, meaning that single key again; private key is a private, only you and the destination or the receiver can know the key; shared key encryption, of course, you share the key with the receiver; and conventional encryption, because this is the first type of encryption. That's why they call it conventional. So encryption is the transformation of data into form that is almost impossible to read without the appropriate knowledge. So meaning that this the original message, you scramble it, you hidden it so that it will not looks like the original message. And decryption is the reverse process of encryption. When the receiver receive, in order to read an original message, you have to decrypt it, or you use the key that used to encrypt it. A key or key pair, appropriate knowledge, how to generate a key and so on, is necessary for encryption and decryption. A key, one key for all. It's like a lot of the ring, one ring for all. This is a one key for all. For this one, this key is used for encryption and also decryption. The same key. Same key. So a key is a digital object. A key is a digital object. It's in the hexadecimal or in the binary. Or this, this is the digital object. So symmetric encryption, a conventional one. So symmetric encryption scheme has 5 components: a plain text, the text you want to send to the receiver, an encryption algorithm. How do we scramble it or hide it so that the original message will not appear like plain text? A secret key to encrypt and decrypt a ciphertext. After your encryption, it will become a ciphertext. And decryption algorithm, how you want to retrieve back the original message. Sender and recipient share a common key. That's why I say one key encryption, one key for all. One key for all. And you have here, security depends on the secrecy of the key. So the more secret, the more you protect your key so that others don't know, or your enemy cannot know, it is more secure. I mean, of course, this key you cannot share. If you share, enemy or any intruders can know what your message, what your file is that you want to send to the receiver. So 5 components: the original message, ciphertext, a coded message, a transform. When you apply the encryption algorithm, it becomes a ciphertext, a secret key, one key for all, and decryption algorithm to retrieve back the message. So you can, this is demonstration of symmetric encryption. So encryption key is QWPRYOO58GJ 10P. This is a digital object, okay? Digital object. So when you apply encrypted message, cache 128, we don't cover cache 128, but we cover something else, but no worries. And decrypted, and you also, if you use the same key, this key, you can receive back the original message. This demonstration of symmetric encryption when you apply the decryption algorithm. When you encrypt the message, this is the ciphertext. This is a ciphertext. And when you decrypt the message, you will get back the original message in original form. You can try this simple demos. So symmetric encryption principle. So A is the sender, B is the receiver, L is Bob, X is the original input, K is a secret key. Both as sender and receiver use the same key to encrypt and to decrypt. Y is a ciphertext, a coded message after you apply an encryption algorithm with the key. And E is the encryption function, D is the decryption function. So A shares a secret key, K with B. So Alice shares a secret key, K with B. Same key for both Alice and Bob. A encrypts a plain text message by applying an encryption function E and the key K to create a ciphertext where Y is EK. Y is equal to encryption function of applying key and also plain text X. A sends a ciphertext to B over a communication channel. Even if anybody other than B get hold of a copy of Y, he cannot decrypt the message unless he has K. Okay, unless the intruder has K, it cannot decrypt the message. It cannot read the original message. It looks like 0123 or XBF, something very weird. Okay, the coded message. If the key distribution is perfect, meaning that A and B really keep their key secret and private, no one knows, or perfect, B does not accidentally or intentionally disclose it, then nobody other than B is supposed to have K. So only A and B have key. On receiving Y, a ciphertext, B applies the decryption function, a reverse process of encryption, and the key K on Y to recover the plain text message. Okay, decryption function X. You want to retrieve the original message X, you must apply the decryption function. And you apply a key and also a ciphertext. So of course, if you try to hide your message, there is also people, or I mean in IT, in science computer, there's always a people try to crack your message, read your message, read your ciphertext. Okay, the process of attempting to discover the plain text, okay, the plain text or key, either you get the plain text, you get the key, is known as a cryptanalysis. The attackers, the hackers. An attacker may try different types of attacks on the encrypted message to discover plain text or secret. So one of the common technique is a brute force. As the name suggests, a brute force. You try every possible combination of key. On an average, a successful rate will require half the number of all possible key tries, meaning that if there is X different keys, on average, the hacker will discover the actual key after X over 2 tries. So X different keys, like 128-bit different keys, maybe 64 tries, okay? Would discover the actual key after X over 2 tries. But it's not confirmed. It's not. It's just a statistical possibility of attackers will retrieve your key after X over 2 tries. It is possible to try 1 million keys per microsecond. 1 million keys per microsecond. Requires only 10 hours to break 56-bit symmetric encryption. 56-bit, okay? To the power of 56 possible combination. Okay? And higher length but does not necessarily make an encryption more secure. So higher length key, you say 128 or 256 or more, does not necessarily make encryption more secure, but it will make it more difficult to crack. Okay, that's why your password, they ask you minimum 8 characters or more. Okay, and in the combination of numbers, capitals, small letters, and character or something like that. It also, it's not just key, it also depends on the encryption algorithm. Both the encryption and the key length is the main we call that is the main principles of a secure encryption. Okay, the key length and the encryption algorithm. So this is type of attacks or encrypted message. Types of attacks: ciphertext only, encryption algorithm, and ciphertext to be decoded. So this is known to the hackers. Okay, encryption algorithm, maybe he knows, and he knows the ciphertext to be decoded. And then a known plain text, encryption algorithm, ciphertext to be decoded, and so on. So you have all this type of attacks. Okay, ciphertext only, ciphertext to be decoded, and then known plain text. If you know plain text, you can also recover the key. Chosen plain text. Plain text. So some of the plain text you can choose a couple numbers of some of the plain text. You can choose so that if you want to recover the key or you want to know the key. Chosen ciphertext is also a part of ciphertext that hackers try to analyze in order to get the key, and chosen text. Okay, so this is required time to break the key. Okay, to break the key from the crypt analysts or hackers. So always possible to trace every key. Most basic attack, proportional to key size, brute force. Brute force, okay? Try every possible combination of key. Assume either know or recognize a plain text. So you have, if key size is 32 bits, it takes about 35.8 minutes for one decryption per second. Time required for 1 million decryption per second is 2.15 millisecond. if this is key bits is very small, and as you increase it from 56 to 168, so you can see that it is beyond a normal computers. Of course, it's beyond our human brain to calculate that, even beyond the normal computers. But who knows? Maybe like the new generation of computers, like quantum computing or super duper computing, they can break. I don't know if that can happen. We are really screwed up. Okay, we are really screwed up. But it's not there yet. I think it's take a very long time in order to have that computer that able to break this in maybe a couple of hours or days. Okay, so we are safe at the moment. So cipher, two types of cipher. Cipher, you want to create ciphertext. So one is the first one is a stream cipher. Use a fixed length key to produce pseudo random streams of bits. Same keys gets you the same stream and XOR those bits with your plain text. In order to encrypt, XOR those same bits with your ciphertext. So this part is simple. You XOR with the plain text to get the ciphertext, or you XOR with the ciphertext to get the plain text. But this is the function you need to know. This is a complicated function. And we have a block cipher. Use a fixed length key to encrypt a fixed length block of data. Process one input block at a time. Okay, the text or the message or the file is categorized, or it is ordered in the block size, fixed block size, and it's produced one output block for each input block, one output block for each input block. Okay, so it's like two blocks, two output, three blocks, three output, something like that. So block cipher overview. Block cipher are functions that take an input message and key in order to create a new encrypted ciphertext. So they take an input message, a plain text, and a key in order to create a new encrypted ciphertext. This function must be a permutation, scramble everything, bits number 1 become bit 7 and so on, meaning a ciphertext can be translated back to the plain text. It is invertible. The function must be invertible, meaning that you from plain text to ciphertext, and it must be able to decrypt the ciphertext so you can get the plain text back. So plain text to the ciphertext and to the plain text back. So this is invertible. Inversion is basically the same circuit with function applied in reverse order, or decryption. Okay, decryption must be efficiently computable. It must, of course, compatible with the hardware and also a software. Okay, the first cipher block. A block cipher is created by a Feistel. So virtually all conventional block encryption, including DS, data encryption, have a structure first described by Horst Feistel of IBM, 1973. Okay, not even you or me, I mean, born yet. The realization, I don't know if you born on 7, you are really old. No, okay. The realization of a Feistel network depends on the choice of the parameters used and the design features. Okay, Feistel network is the basics one. So Feistel operations, if you split the plain text block into two equal pieces, so you have left and right. Okay, the plain text. N rounds of processing for each half before going to produce a ciphertext. For each round, the left encryption is equal to the right encryption of the previous block. Okay, and right encryption of the current block is equal to left encryption of the previous block, XOR with the encryption function of the current key, and of course the right plain text of the previous block, where f is the round function and ki is the subkey, and n round the ciphertext is len and ren. Left ciphertext of n round, right ciphertext of n round. Decryption is simply the inverse of encryption, following the same steps as above but reversing order in which the subkeys are applied. So this is basically a Feistel cipher structure. So you have this. This is what I mean by this is the input plain text. You divide by 2, left and right, round 0, round 0. So round right plain text of round 0 will become the left plain text of round 1, while the left round 0 plain text will XOR with the encryption function that apply the key as well, so that it will become the right right ciphertext of the round 1, and so on. And then the decryption is the reverse process. Okay, so right encryption and right encryption, always right encryption of previous block will always be a left ciphertext of the next block. So that's it. So Feistel cipher parameters. So it depends on the block size. Larger block size means greater security. Key size, larger key size means greater security. Number of rounds, multiple rounds offer increasing security, typically 16 rounds. Okay, 16 rounds typically. Can have 10, 14, or 16. Subkey generation algorithm. Greater complexity will lead to greater difficulty to cryptanalysis. So subkey generation, if it is a complex subkey generation, it will become more difficult for attackers to retrieve the keys. A round function, greater complexity means greater resistance. So a round function, I mean, if you have many rounds with a complicated or complex encryption function in that round, meaning that it will offer greater security or greater resistance. So the previous one that enjoy a successful and commercial encryption is the data encryption standard. It is the most widely used encryption scheme until now. The algorithm is referred to as data encryption algorithm (DA). So algorithm is DA, data encryption algorithm. The name of the encryption is data encryption standard. So it processes 64-bit blocks. And from 64-bit blocks, the key is 56 bits. So you have a 64 bits key, and then you drop 8 bit, you have a 56 bit keys. 8 parity bits are stripped off from the full 64 bit key, 8 characters. So you have a 16 sub keys created for 16 round. Okay, key 1, key 2 until key 16. So you have a 16 sub keys generated. So in a today's processing power of the computer, it is proof insecure with 56 bit. So DS basic function is diffusion and confusion. So the simple level diffusion is achieved through numerous permutation. Bit 1 become bit 17, bit 2 become bit 16, and so on. And confusion, where you apply XOR operation to make it more confused, to make it more complex. So permutation, a binary word has its bits reordered. Permute, meaning that bit 1 become bit number 13, let's say bit 2 become bit number 13, bit 3 become bit number 27, and so on. It is also known as a P box. For example, first bit may become 7 bit, second bit 12 bit, and so on. Substitution. So binary word is replaced, substituted by some other binary word. It is also known as a substitution box or S box. In practical, to build a 64-bit blocks, multiple X boxes of smaller blocks are used. So let's say for an input 011001 to an X box, the output may be 1001001. So if you apply this one, a 6-bit, it become a 4 bits for the X box output. So this the basic diagram of this encryption and decryption. So here you have a 64-bit plain text, and you apply 56-bit key. This is a DS cipher, and then you get a 64-bit ciphertext. And for the decryption, 64-bit ciphertext, you apply the decryption function with the inverse, which is inverse of encryption function encryption function in the reverse order, and you retrieve back the 64-bit original plain text. So this is DS encryption structure. So 64-bit plain text, you have, and then you apply the initial permutation box, and you have round one, you apply the K1, 48-bit K1 key 1, around sub key, K1, sub key K1, sub key K2, and sub key K16 for round 16. So this is from the 64-bit. Drop 8-bit, you have a 64-bit cipher key. Round key generator, you drop another 8-bit until it becomes 48-bit. You apply on the this encryption function. So this is like, okay, this is a permutation. Okay, bit number 1 until bit 64. Okay. 1, you become 40. 1, the original plain text bit 1, it you reorganize, you put at number, you put at location 40, and so on, 2, 8, and this one. So initial permutations, put 60 rounds of encryption standard, and you have a final permutation. So this is initial permutation. 58, 50. So this is the first 1, 2, 3, 4, 5, 6, 7, 8. First 8 bits, second 8 bits until the 8 bit, sorry, the first 8 bits until the last 8 bits here. Okay, in a group of 8. Okay, let's say you have a find the output of initial permutation box when the input is given in hexadecimal. M is a plain text. M16 0x00. Okay, M16 is a plain text. If you zero in computer, they always sometimes you get an error. Okay, error violation on 0x blah 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 blah. This means that x is a hexadecimal. It is an M16 in 16 base number, hexadecimal. 0000008000000002. Okay, I'm not sure whether you know 00000000010010 until 1111. This one is 0 and this one is 15. Okay, so you have a 00, sorry, not 15, F. 0, 1, 2, 3, A, B, C, D, E, F. Okay, F. So you have 000000080. So you put here 0 here is 0000. 8 is 1000. I'm not sure whether you I hope that you know this. This is a 2 to the power of 0. 0 times 2 to the power of 0, 0 times 2 to the power of 1, 0 times 2 to the power of 2, and 1 times 2 to the power of 3. So that's why it becomes 8. I assume that you know this, everyone. Okay, and you know the table how to convert the hexadecimal to the hexadecimal from this is a binary number, this is the hex. Okay, you know the table hex to F. Hopefully you know because you will use a lot of this, and of course you know how to convert. Okay, from this table you know how to convert. So this one is 000. You 0 here, 4 bits 0, hexadecimal 0 is 0000 in binary number, base 2 number. 0 here 0, and then 8 is 1 and 2 is 0010. Okay, you use where's the initial permutation. Okay, we are interested in initial permutation. Where is it? Only bit 25 here, bit 25, and bit 37. Sorry, bit 25 and bit 63. This is bit 63. Okay. When you convert to base number or binary base 2 number or binary number, you only have 0 and 1. Okay. You only have 0 and 1. So only bit 25 and bit 63 are ones. So if you look at the initial permutation is 8, where is bit 25? Bit 25 is, where is 25? here 25 initial permutation. So this one 8, 16, 24, 32. The original bit number 25 here become bit 37 in the initial permutation. You apply the P box. You apply to P box to M2. Apply the P box to the encryption. You apply the P box to the plain text that already convert to the binary number or base 2 number. And then you have the initial permutation M2. So bit 25 here become 37 and 63 become 57. If you use 63 here and 57, this is 37 and this is 57. The original bit location you scramble around. So this is the initial permutation. So you get here initial permutation of M2 is this one. You convert back to the hexadecimal, it becomes 0, 8 and 0080. This one is 8 and this one also 8. 4 bits. Okay. Initial permutation, you convert back to 16 base number or hexadecimal, you have this. Everyone understood this one? Just recalling back your binary stuff, truth table.
Hello,
Yes.
doctor.
Yes.
Hello, doctor. Can you repeat, because I don't understand from the permutation table. How do you get bit 25 becomes bit 37?
Oh, bit 25 become bit 27. Okay.
Yeah, from the table. Thank you.
From the table. Okay. Okay. This is bit number 1, 2, 3. Bit 1, 2, 3, 4, and this is bit 64. Okay. Wait, we just erase everything. Of course, some of the programming language you already have library for this. You don't need to know this. Of course, if you do a programming language, they have the library. Most of the standard programming have a library for ASDS. But of course, for this course, you have to know the fundamental. You have to know what is behind that, how to build this. What build this so that it become a library. You can use. In a programming language, you just use a 1, 2 lines to convert all this to DS. But if you do, in this course, you have to understand what's behind that. How do they put the encryption and decryption algorithm? Okay. So you have here, this is M16. This is in a hexadecimal. Hexadecimal. So if hexadecimal is 0000, 0001, 0010, 0011, 0100, 0101, 0110, what else? 0111, and then 1000, 1001, 1010, 1011, then 1100, 1101, 1110, and 1111. So in hexa, this is in the binary or base 2, binary number M2. Base 2, binary. So in hexadecimal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay. 0 to F, 16. 0 to F is 16. That's why you call it M16. This is a plain text. PT16 or whatever. I just use the example is M16. Message. The message is something else, and then when you convert to binary, you convert to the hexadecimal, it become this one, and you convert to the binary number, it become this one, M2. Binary number base 2, 0 and 1 only. Okay, look at this box, initial permutation. This bits number 58 become the first bit. Or the original plain text, bit 58 become the first bits. Bits 50 in the original plain text become bit number 2, 42 and so on. 25 become 37 and 63 become 57. And 57, this is 37. So you convert here. Only bit 25 and bit 63 are ones. Okay, this is the original plain text, original message. Only bit 23 and bit 63. All this is 64 bits. So 23 become 25. Sorry, this is 25. Sorry, 25 becomes bit 37 in the. After you apply this box, initial permutation or IP, you apply IP, initial permutation, to the message. So bit 25 become bit 37 and bit 63 become bit 57. This one 63 become 57, 25 become 37. Then you convert back to hexadecimal. It's not necessary to convert back. Just to show you, you convert back to hexadecimal. 0 is 0. And then you see this one 1000 is 8. This one you put 8. And 1000 put 8 as well. So you have 16 hexadecimal characters. 4, 8, 12, and 16 hexadecimal characters. Do you understand? Do you can understand this one? Never mind. That's why you have to practice. We'll give you some assignments to play around, and you can play around with the software as well. Or if you can use any language, programming language. I mean, you can do your assignment manuals, or you can use programming language. Any programming that have a built-in library for all this encryption standard. So this example, okay, this is the after the conversion using the initial permutation, the plain text, initial permutation plain text. 0 is in the if 16 hexadecimal, okay, 0000, 0000, 0800, and 0080. This is in hexadecimal. Prove the initial and final permutations are the inverse of each other by finding the output of the final permutation if the input is this one. Okay, this is the initial permutation. So if you convert to binary, only bit 37 and bit 57. Sorry, is it 37? Yeah, it's 37 and 57 is 1. So if you apply the final permutation box, this is the final permutation box, okay? FP. You apply the FP box to the initial permutation of original message, where is bit 37 become 8, 16, 24 become bit 25, and 57 become bit 63. This is actually the final permutation. This is bit number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until 64. Okay, bit 63 and bit 37 become 25 and 63. So if you apply the final permutation box into this the previous initial permutation message of message, you will get the final permutation and you retrieve back the original message. M16 0000080000002, which is the first one, the original. So initial permutation and final permutation is the inverse of each other. The IP box and FP box, initial permutation and final permutation, are the inverse of each other. Inverse, meaning that this for encryption, this for decryption, or something like that. So you can retrieve back the original message by using only IP box and FP box. First, the original message, you apply the IP box, initial permutation, it become IPM, and you apply the FPM here, FP final permutation to the IPM. You apply the final permutation and you will retrieve back M. So this the original message. Apply initial permutation, you have IPM, and then you apply the final permutation on the IP initial permutation message, and you can retrieve the original message. So it shows that final permutation is the inverse of initial permutation. This is just the beginning. This is just the beginning of the encryption. It's not yet. You haven't go yet to the this scrambled confusion or diffusion box. So the initial and final permutations are straight permutation boxes that are inverse of each other. This is a conclusion that you can give on the initial permutation and final permutation box, or straight permutation boxes. They are inverse. They are inverses of each other. Final permutation is inverse of initial permutation. Initial permutation is the inverse of final permutation. They have no cryptographic significance in DS. This is just the beginning, okay? There's a little bit of cryptography because they scramble bit this and that everywhere. But they're not really significant cryptography in DS. So this not even round one yet. Not even round one yet, that one. So this it becomes more interesting as you go along the slides. So DS uses 16 rounds. Each round of DS is a Feistel cipher. Okay, this is the plain text where I informed you before. You have to 30 if plain text is 64 bits, and you have to rearrange the left plain text and right plain text. Okay, left plain text and right plain text. And then you apply a mixer. This is a XOR, this is a round function, and this is a swapper. We will look at this one by one. Okay, give you some example. So the heart of DS is the DES functions. This is the DS function which includes expansion P box. From 32 bits plain text, you have 48 bits encryption in plain text after you apply the expansion P box, and you XOR this with the key K1 48 bits, and then it becomes 48 bits. And then you apply the substitution boxes, it reduced down to 32 bit backs, and then you apply the straight permutation box, it becomes 32 bits, and this is the out round one. Each round you do the same process all over again. Each round you use the same process. So this is the expansion permutation box. Since R is a 32-bit input, the right plain text, I assume I is 1, round 0, R0, is a 32-bit input, and K1 is a 48-bit key. We first need to expand because K is 48-bit, and the round plain text, right plain text, the right portion of the plain text is 32-bit. You first need to expand. Either you expand right or you reduce down the K. But in DS you expand the right. You expand the right plain text. Right, around 0 to 48 bits. Although the relationship between the input and output can be defined mathematically, the SU structure and table to define this P box. Okay, you don't have to know the mathematical equation behind that. If not, it's gonna be a purely cryptography courses. Okay, this is a cryptography. Just this. You just have to know how to read the boxes, how to apply the boxes. Okay, so you add from this 32 bits, write plain text. You expand to 48 bits. So bit 32, where's bit 32? You add for the first bit, and bit number 5 here, you become this one. So you expand bit 32, you put here, bit 5 put here, bit 9 you put here, bit 13 you put here. This one bit 4 you put here, bit 8 you put here. So it becomes 48 bit plain text. Okay, 48 bit plain text. So the black arrow is the original plain text, original right portion of the plain text. And then you apply, you add, okay, bit number 5 here, from bit 32 you put here the first one, and bit number 5 you add 1. So this one from 4 becomes 6. 6 times 8 for 48 bits. So from 32 bit input you become 48 bits input. Sorry, output. Okay. Again, this is a fun part. Of course, I use this example use more zeros than one. Okay, you have a message or plain text. M is a plain text. You have a message. This is the original message. After you apply the initial permutation to the message, you have this. Remember, this is in the hexadecimal. So from the initial permutation of the message, you divide equally. This is all okay. This one convert to binary. So you convert to binary, you have 64 bits. This is 64 bits. 64 bits. So this is the left 0. This is the right 0 round or initial stage. So the left is 0, L0, we call left 0 and right 0. Okay? You divide equally. Then you apply the expansion P box. Okay, the expansion P box. So 1, 2, 3, 4. So this is the original. Okay, this is 1. Okay, let's say 1, 2, 3, and 4. This 4 bits. This the first 4 bits. 0, 0, 0, 0. So bit number 5, bit number 32 you put at the beginning. The bit number 32 is 0. So you put here 0. And bit number 5 here is 0 as well. So you become here 0. 0, 0, 0, 0, 0, 0. Okay, first, of course, you divide this the left portion, this the right portion. And then you apply the expansion, this one. Sorry, 0, 0, 32, 5 is 1. Oh, right, sorry, this is right, not left. You apply the right portion. So bit number 32 is 0, but bit number 5 here, 1, 2, 3, 4, 5 is 1. So you apply here 0 and 1. You add, this one is 0 and this one is 1. This one is 0, 0, 0, 0. Okay. And this one is 1, 0, 0, 0. Okay, this one is 1, 0, 0, 0. This is number 2. Okay, 1, 0, 0, 0. And then you apply bit number 4 here. 1, 2, 3, 4 is a 0. Bit number 9 here is 1, 4, 9 is also 0. So that's why you have 0, 1, 0, 0, 0, 0. 0, 1, 0, 0, 0, 0. So you apply the, after original message, apply the initial permutation, and then you apply the expansion P box. You have this. The expansion P box of the right portion plain text after the initial permutation is this one. So after the expansion permutation, DES use the XOR operation on the expanded right section and the round key. So you have here, remember, you have a 32 bits input. First you have 32 bits input plain text, and then you expand to 48 bits. This is 48 bits. Terrible handwriting, sorry. And then you XOR here. Sorry, XOR is plus. XOR with key. Key 1, which is also 48 bits. So same bits you can XOR. After the expansion permutation, DS use the XOR operation on the expanded right section. Expanded right section, okay? You remember this is the initial permutation of the plain text. You divide into left and right. Concentrate on the right portion, and then you apply the permutation box. You apply the expanded permutation box, and then you have this expansion of right portion and the round key, and you XOR with the round key. So note that both the right section and the key are 48 bits. Now you have the same bits that you can XOR. So altogether is a 16 subkeys generated for 16 rounds. So subkey 0, subkey 1 used in the round 1. Subkey 2 used in the round 2, and so on. So in overall you have 16 subkeys generated. Then you have the S boxes. The substitution boxes or X boxes do the real mixing or confusion. I hope that you are not confused up to this stage. The substitution box, okay, everything this is for the hackers, to make it difficult for the hackers to retrieve the original message. That's why you're mixing around, you add this bit and stuff, you substitute, you everything, you do a permutation, this one just to scramble your original message so that the hackers cannot easily retrieve the original message. Say this DSX boxes, the substitution boxes or X boxes do the real mixing or confusion. So DS use the 8 S boxes, each with 6-bit input and 4-bit output. 6-bit input and 4-bit output. So you become a 48. You apply a 48-bit input after you XOR with the key. You apply the X box and become 32-bit output back. So bit 1 and bit 6 on the row. Bit 2 and bit 4 is on the column. So this one is 2 bits. 2 bits, so 2 to the power of 2, only 4 output, okay? 0, 1, 2, 3, 2 to the power of 2. And for the row is 2 to the power of 4 bits, 1, 2, 3, 4. So 2 to the power of 4, 16. So that's why you have 0 to 15 or 16. 16 output. Okay? So table below shows the permutation for X box 1. X box 1 or S1. So if your bit 1 and the first bit and the final bit 0 0, this one is 0 0 0 1 1 0 and 1 1. Okay, 0 0 0 1 1 0 and 1 1. And this one is 0 0 0 0 0 0 0 1 0 0 1 0 until 1 1 1 1 1 1 1 0. Okay, this is the Xbox One or S1. So if you're 00 and then 00, you have 14. 14 in the decimal number, you have to convert to binary number. Okay, the input to Xbox One is 100 10011 So what is the output? So you see here one, okay, the first and the last bit is 1 1. So the row is 1 1 and 0001. Column is 0001. This one you convert to the decimal number 3. This one you convert to decimal number is 1. If we write the first and sixth bit together, we get 1 1 in binary, which is 3 in decimal. The remaining bits are 001 in binary, which is 1 in decimal. So we look for the value in row 3. Row 3. This is row 3. Row 3 and column 1. So we have here 12. Row 3 and column 1. The result is 12 in decimal, which is in binary is 1100. The binary is 1100. So the input 010 yields the output 1100. So this is an Xbox example. So the Xbox is 0000. So you put here 00. Row is 00. Row 0 and column 0000 still 0. So the first one, we get 00 in binary row, and this one is column. So you look at 0 and 0. 0 and 0, 14. In decimal is 14 in decimal is 1110. So the input is 00000 yields the output 1110. Of course, this is the first 6 bits. The second 6 bits. This is the second 6 bit. You apply the S2 box. The third 6 bit you apply the S3. Yes.
Yeah, Dr. Questions. When we do this computation, right, does it mean that where the a 6 bit is being decoded to a 4 bit, right? Isn't
yes. Because
data?
okay, yeah. No, it's not a loss of data. The DES is created so that you will not lose data. You just add the bits, expand and compress, You will not lose the data. If you lost the data, meaning that your data DES lost the data, meaning the data is corrupted.
Oh,
Okay. But DES is created not to lose the data. You just play with the bits 0 1 1 0. Okay. So the S1 is for the first 6 bit, S2 is the second 6 bit, S3 for the third 6 bit, and so on. So you apply for the S1, B1 for the first 6 bit, second 6 bit, and the 8th 6 bits. SIBI refers to the output of Xbox. And you have the straight permutation table. Okay, you have a straight permutation table in the DS. Again, from that 32 bits, you apply this as a straight permutation table, you will get the 32-bit output. Okay, you will get the 32-bit output. This is only for the plain text. This is for the function of plain text. And this is the function of the keys. Remember, plain text and the key is a different things. Plain text and the key are the different things. So this one is for the plain text, and this one for the keys. And of course, you across each other, you have to XOR the 32 bits XOR with the 48 bits. The 48 bits plain text after a round function, straight permutation table, and then so on. You XOR with the key. The key original is 64 bits. Do a parity drop, apply a key permutation box. You have a key bits of 56. And then this is the process. Okay, this is the process or algo. Do you need a break, everyone? I want to continue.
Yes.
Okay. All right. Yeah, it's like raining. You can hear the raining. Okay. We take break about 20 minutes, refreshing, and then those Muslim you can pray. I think it's already Maghrib. Okay, see you in like 7:40, 7:45.
Thank you, Doctor.
You're welcome.
Thank you.
Okay, everyone, shall we continue?
Yes, Doctor.
Yes.
All right. So, okay. Previously we have talked about the symmetric encryption, general symmetric encryption, and then on the Feistel Cipher and the plain text algorithm in the DES, the data encryption standard. So now we go to the data encryption standard sub-key generation. Okay, as I mentioned before, each round key sub round key generation has a different for each have a different we call that different input for each round. Okay, key for round 1 is not the same with the key round 2 and so on. So the first key include a 64 bits. Okay, and then you drop 8 parity bits. Of course, we have a table, this one, and then it becomes 56 bits. And from 56 bits here, you divide equally half of it, 28 bits left and 28 bit right. And then you perform a circular left shift for both left and right. And then you combine both keys so that it becomes 56 bits 50 bits back. And then you do a compression permutation, you drop another 8 bits, so it becomes a sub key 48 bits. Okay, from 64 bits become 56, divide by half, and then from 56 bits you become a 48 bits. Rotate the bits left by single bit. Okay, let's say 0 1 0 0. If you rotate to the left, it will become 1 0 become this one, and this one become here, and it become 1 0 0 0. So this is the left by single bit, rotate left. So 1 become the first bit, the third one become second, the fourth one become third, and the first one become the last bits. And from 48 bits, you add with 48 bits of plain text. So 1 bit shift for round 1, 2, 9, and 16. 2 bit shift for round 3, 4, 5, 6, 7, other than 1, 2, 9, and 16. Okay? 1 bit shift and 2 bit shift. This is for the circular left shift operation. Circular left shift operation. So key permutation, parity bit drop. The keys are actually stored as being 64 bits long, but every 8 bit in the key is not used. Bits number 8, 16, 24, 30, 40, 48, 56, and 64. So so you drop bit number 8, 16, 24, 32. So from the original key, from the original 64 bits key, 8, 16, 24 in a step of 8 bits. You drop this, and then you apply the parity bit drop table. The 57 bits from the original key become the first bits, and so on. So number of bit shift is for round 1, 2, 9, and 16, 1 bit shift. Other than that, it's a 2-bit shift. Okay, let's see the example of subkey generation from the original 64-bit key. So key in hexadecimal is 133457799BBCDFF1. Okay, so 1 hexadecimal you convert to binary 0001. Okay, 0001, 3 0011, 1 and 3. 3 is 0011. Then 3 again 0003 again 0011, and 4 is 0100. So you convert all this to the binary number, hexadecimal to binary. So you get here all 64 bits. You group into 8 bits per group. So you have 1, 2, 3, 4, 5, 6, 7, 8. Okay, you group in 8 bits per group. So you apply the key permutation or parity bit drop table here. This one, parity bit drop table, you apply to that key 64 bits, so that it becomes 56. So we get 50 bits. So the bit number 57 is bit number 57 will become the first bits. So this one 8, 16, 24, 32, 40, 48, 56. This one 57. Bit number 57 here will become the first bit after the parity bit drop table. So bit number 49 will become bit number 2. So 49 is 6, 49, 56, 48. This is 48, 49 also 1. So 1 will become bit number 2 here, and so on. So you have here K. After this is 64 bits, this is 64. Now it becomes 56 bits. Next, split this key into left and right half, so that we have a C0 and D0. Key left and key right. So C0, so 1, 2, 3, 4. So you break into half. So 1, 2, 3, 4. So this one will become C0 and this one become D0. C0 and D0. The left and the right. So from original pair C0, D0, round 1. Okay, you have here where's C0? Okay, C0, D0 here. And then for round 1, number of left shift is 1. So from here 1, okay, you look at C0. Okay, all this move to the left. All this move to the left. This one moves to the last one. This one, all this move to the left. Okay. So you get C1, the new C1, round 1 subkey, you become 1, 1, 1, 1. This one, instead of 3, 1 at the beginning, you become, instead of 4 ones at the beginning of the round 0, you become 3, 1 here. And then here you move also left. This one you move to the left, but at the end. And then 0 you move here, so it become 1, 0, 1, 0, 1, 0, and R1. So for round 2, also 1, again, move to the left. But round 3, move 2 bits. You see 1, this is 1, 1. So you have moved 2 bits here. This one here, and this one here. So you have 2 bits move here, and 1, 1 at the back. 1 here at the back, 2 bits shift, and following this until round 16. I just show until C3 because I show until C3 because this is the first of the number of left shift bits, starting with 2 left shift for round 3. And then round 9 is only one bit rotate, 1 left bit shift, and round 16 1 bit left. So now we have, after we have that, we have 56 bits to 40 bits key. You apply the key permutation compression table. You don't have to worry about all this table. It will be provided in the final exams. And of course, for your open book, you can always refer this. So you don't have to memorize. No one memorize this. Okay, they have a mathematical background in developing all this table. You don't have to worry about that mathematical, and you don't have to memorize all this, but you must know how to apply this, each table, each box. Okay, each table and each boxes, you must know how to apply it in the DES. So this one from 56 bits to 48 bits key. So again, you group in a 3, 4, 5, 6, 7, 8 in the group of 8. So from 56 you become 48 bits. Okay, for the first and second key, we have 56 bits. So C1, D1, you combine left and you combine the left one and you combine the right one. This one is 111. Okay, this is a 56 bit, 56, and of course this one is 56, which after we apply the permutation compression table become 48 bits. So K1 is, after you apply K1 become this one, C1 D1 become K1, C1 D1 become K1, and of course K2 and K3 you apply the 56 bit, you apply the permutation compression table here. Bit number 14 will become bit number 1. So let's see which is bit number 14. 8, 16, so this is bit number 14. 14, 1. So 1. Wait. Is this correct? Wait. 14, 56 bit. 3, 4, 5, 6, 6 times. Bits number 14 become number 1. 8, 9, 10, 11, 12, 13, 14. Wait, this one. 8. Somewhere is wrong here. Wait. For others key, we have K2, bit number 14 here. Yes.
I think that is a 12th position you are considering, Doctor.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
That is 12.
Sorry,
Yeah.
14. 1, 2, 3, 4, 5, 6, 7. Okay, sorry. I thought this was 8. Sorry. This one 7. Sorry, 7. Okay, never mind. This is 12. This is 14. Sorry, correct. Yeah. Sorry, my mistakes. So 0 become the first bits. Here 0 become the first bits. Bit number 14 become the first bits after we apply the permutation compression table. And same with the other round as well. So again, this is a summary of the DS encryption. So 64-bit plain text, you done the initial permutation. Round 1, you add with the key sub key. Round 1, 48 bits. So this is in the each of the round. This is for the plain text. Okay, for the plain text part. This is what the round function is. You have a mixer and you have a swapper. You swap. Okay, you swap, and this will become for the round 2 input. And this for the key. You K1 you XOR with the you XOR with the plain text. Okay, you XOR with the plain text. So this some summary. This is the overview. This for the plain text. For the K1 here, key K1, you XOR with this function R1 K1. You add this one and then you mix with the left and then you swap. This will become the input for R2. This is for the keys. So it looks complicated, but this it can easily be broken with the today's technology of computers. Okay. The major criticism of data encryption standard regards its key length. The key length 64 bits is too short. Okay, it's too short. Bitcoin hash, if you look about Bitcoin SHA-256, they use a 256 bits secure hash algorithm. So in modern computer, 64 bits is considered short. Fortunately, there are a number of alternatives to DS. This means that we can use triple DS to increase the key size. So another, like you just expand the DS into a triple DS so that you can make it more difficult for hackers to break the key or retrieve the secret key. So triple DS is just DS with two 56-bit keys applied. Given a plain text message, the first key is used to encrypt the message. The first key is used to encrypt. The second key is used to decrypt the encrypted message. Since the second key is not the right key, this decryption will scramble the data further. So this is not the same key, okay? The second key is not the same key. The second key is not equal to the same to the first key. If it's equal, you can retrieve the original message. The second key is others key. It will further scramble the message, become more confused. The bits are pretty much everywhere. The twice scrambled message is then encrypted again with the first key to yield the final ciphertext. So key 1, then you use key 2, you encrypt, you decrypt, then you encrypt back with key 1. The twice scrambled message then encrypt again with the first key to yield the final ciphertext. So the last one, it became the ciphertext. Triple S just DS done 3 times with 2 or 3 keys used in particular order. You can also use a different keys K1, K2, and K3. So it doesn't matter. It's just expansion of standard DS. So here you have a DS cipher, reverse cipher, the decryption in encryption, and you encrypt back. Then you have a 64-bit ciphertext. You apply key number 1, key number 2, and key number 1 back, or this one can become also key number 3. It's just whichever design that you prefer. So basically, it's just doing a triple DS, make it more difficult for hackers to retrieve the keys or original plain text. So this is a triple DS with 3 keys. So you have K1, K2, and K3. You have a ciphertext. And for the decryption ciphertext, you apply K3 first, the key number 2 and key number 1, and you retrieve the plain text. This is triple DS operation with 3 keys. This is a triple DS operation with 2 keys, K1, K2, and K1. This one is K1, K2, K3, and reverse K3, K2, and K1. So the use of 56-bit key for DS, again 56-bit key rest, threatens so speed of commercial now become more processor, become like you have a multiple CPU, multiple core in processor, in computer processor, you can you can execute or you can run the program faster. If you want to run to hack using the brute force program, the 56-bit, you can easily retrieve maybe in I know couple of hours or maybe minutes, who knows, with the advance of the hardware. Triple DS enjoyed widespread use for few years when they found that DS with the modern computers increase has a higher performance, higher speed. They introduced triple DS, and triple DS able at that time to overcome this the problem of basic DS. But triple DS has a severe drawbacks or has a couple of problems. Slow in software because you have to apply 3 times. It's also uses 64-bit block size. A larger length is desirable for efficiency and security. So the larger block size is deemed necessary in today's computer performance, so that it will have higher efficiency and also in security wise, it is much more difficult to break. So in 1997, US National Institute of Standards and Technology, or NIST, officially endorsed advanced encryption standard. So DS, you cannot use DS anymore. It's still being used a smaller in some of it still use triple DS, but NIST endorsed the advanced encryption standard, or ES, to replace DS based on the security, the computational efficiency, memory requirements, hardware and software stability, and also a flexibility. So all the problems of DS is fixed using the AES, which is of course advanced. When the name advanced, is much more difficult to break, much more complex algorithm. Okay, much more complex, but it also a faster and more efficient. So advanced encryption developed by John Damon and Vincent Richmond from Belgium. So sometimes it's also known as Rijndael algorithm. So the algorithm use 1 to 8-bit block. DS use 64 bits block. What is 1 to 8? So DS use 64-bit. The S use 1 to 8-bit block cipher. It's still a block cipher with 3 different key length: 128, 192, and 256. So DS use 64-bit and with reduced down to 56-bit DS. So for the AES, use 128, either 128, 192, or 256 bits, and it supports 10 to 14 rounds. So design is simplicity, flexibility, efficient, and fast for both implementation in software and hardware, and code compactness on many CPUs. It works fast even on small devices such as smartphones, smart cards. Okay. AES provide more security due to larger block size and longer keys. AES use 1 to 8-bit fixed block size. 1 to 8-bit, there's no fixed block size, and work with 1 to 8, 1 and 2, and 256-bit of keys. Example, we use 1 to 8 bits. It also offers a lot of other flexibility, like AES in general is flexible enough to work with key and block size of any multiple of 32-bit with minimum of 1 to 8 bits. Okay, multiple of 32 bits and maximum of 256 bits. So its security is resistant to power analysis and other implementation attacks. If you want to apply a brute force attack or others attacks, it's much more difficult. The crypt analysis is not that simple. So advanced encryption standard, this is the main properties: block size 1 to 8-bit block size, number of rounds 10, 12, or 14. Just assume 10 rounds for brevity. So for simplicity, we will use a 10 rounds example. Okay, the key size is 1 to 8-bit or 4 words or 16 bytes. 1 word you have 32-bit. We will look at the example. Number of subkeys is 44 subkeys, or 52 for 12 rounds, or 60 for 14 rounds. The 10 rounds is 44 subkeys. In DES, you have only 16 round. With 16 round, you have 16 subkeys. DES. Each subkey size is 32-bit or 1 word or 4 bytes. Each round have 4 subkeys. Even in each round, you have 4 subkeys. And pre-round calculation, you have, okay, before you enter round 1, you have a pre-round calculation. You have 4 subkeys as well. So overall, you have 44 subkeys. So the AES encryption process, the cipher consists of n rounds. Maybe you use a 10 rounds, assume 10 rounds, where the number of rounds depends on the key length. 10 rounds for 16 byte key, 12 rounds for 24 byte key, and 14 rounds for 32 byte key. The first n minus 1 rounds or 0 rounds consists of the first n minus 1 rounds consists of 4 distinct transformations. Round 1 until round 15, round 1 until round 9 consists of 4 distinct transformations: sub bytes, shift rows, mix columns, and add round key. Sub bytes, substitution bytes, shift rows, shifting left, right, mix columns, and add round key. The final round n contains only 3 transformations. They don't have a mixed column for round number 10 or the final round. Each transformation takes 1 or more 4 times 4 matrix as input and produce 4 times 4 matrix as output. 4 times 4 matrix. Key expansion function generates n plus 1 round keys, each of which is a distinct 4 times 4 matrix. So you have here, you have to do a multiplication of matrix. So advanced encryption standard use block to state and state to block transformation. So you have a block B0, B1, B2. This block 1 to 8, meaning that 4. Sorry, 8. 8 times 16. 1 to 8. So each block, and then this one is block in the block diagram. You transfer to the state diagram, which one? BU0, B1, B2, B3, B4, B5, B6, B7, and B8, B9, B10, and B11, and this one. So this is insertion and extraction flow. B0, B1, B2, B3, B4, B5, B6, B7, B8, B9, B10, B11, and B12 until B15. So this one is the matrix 0001, this location of the matrix, and you transfer back to the block size. If you can easily transfer back to the block diagram. So this is this one of the simplest AES. Assume that text block is AES uses a matrix. So AES uses a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But in original, what we call that, a null character also is considered as a character. But this, for simplicity, we just use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you add another like bogus ZZ. In order to complete a 16 character, you put a ZZ at the end to get 16 character data block. And replace each character with an integer between 0 and 25. So A is 00, Z is 25. This is just some example. But in the data communication or in computer, if you want to convert a character A, Z, whatever, or numbers or other character like $sign, #, you use a ASCII code, ASCII, ASCII code. But never mind, this for A until Z, assume A is 00 and Z is 25. So this is state matrix. State matrix. This is a block. AES uses a matrix ZZ to make it 16 character data block. This is a block. Okay, this is a block. And then you convert to hexadecimal. A is 00, Z is 25, E is 4. Okay, this is A, B, C, D, E. Is 0, 1, 2, 3, 4. E is 5, 4, and so on. And you convert this to the state from block. You convert all this to the state 0, 0, 4, 1, 2, and 1, 4. 1, 2, 0, 4, 1, 2, 0, 4, 1, 2, 0, 4, 12, 0, 0, 1, 2, 0, 4, 12, 0, 0, and so on. So this is the block and this is the state. This is a simpler example, but in the real you have to use an ASCII code to convert a character AZ numbers or other $sign hash sign using the ASCII table. So data block of 4 columns or 4 bytes is state. Key is expanded to array of 32-bit words. We look at example of this 32-bit words with number of subkey corresponding to 10, 12, and 14 rounds. 44, 52, and 60. So again, just to recall you back, 32 forwards. One word is 32-bit. Forwards is 32 times 4, 128. 32-bit words. So has n minus 32-bit. One word is 32-bit words. 32-bit words. Oh, sorry, 32-bit words. 32 a key is meant to array of 32-bit words. 32-bit. And has n minus 1 rounds. Identical rounds in which state undergoes byte substitution, shift rows, mix columns, and add round key. The final rounds or round 10, they don't have a mixed column. Mixed column also is not needed for the last round. You can see here, the final one doesn't have the, is this one? I don't know. Oh, this one, yeah. So you have a cipher key W0 word 0 until word 3, 4 bits, 4 bytes. W0 until W3. And then you have 44. Overall, you have 44 round keys. And then you have a plain text, sub byte, shift row, mix column, and add round key. Everyone. And then ciphertext is this you will produce ciphertext, and then the decryption again is a reverse process of encryption. You have a plain text, you have this is a plain text, and you have a key expansion as well. This is quite complex compared to DES. So AS single round, you have a state. You apply the sub bytes, you have a different, you have again state. You apply a shift rows, you have a state. Mixed column, you have a state, and then you add the round key from the key expansion, and it will produce a state for each round, single round. One add round key is applied before the first round. The third transformation is missing in the last round. So the third transformation is missing in the last round. The mixed column. So this is the first transformation, second transformation, third transformation, and fourth transformation. But the mixed column in the last round, round 10, we assume round 10, you remove the mixed column transformation. Okay, step-by-step solution of AES. Given the plain text, key, and ciphertext. Okay, this all in a hexadecimal. Okay, 1 to 8 bits. Okay, 32 times 4. Yeah, 32 times 4. This one is plain text, and this one is the key. So you have plain text here, and you have a key. Okay, we are going to solve the key generation up to round 1 only. Okay, given a plain text. Okay, this you have a plain text and you have a key here. So plain text and a key. So you have first you have a key expansion. Again, same with DS, you have to differentiate between the plain text process and the key process. But in a way, you have to XOR the plain text and a key. XOR plain text and a key in certain process. Key and plain text will meet each other with the XOR. So steps, key expansion, you talk about the key, okay, key. Put in 4 words, each word is 32 bits in a group of 8 bits. Rotate W3, word number 3, word 0, you have word 0, word 1, word 2, and word 3. Alright, rotate W3, the last word with 1 shift to the left, the new column will become X1. So if you rotate W3, it will become a new function of X1. Use sub-byte box to bits rearrangement. So X1 will become the Y1 function. From X1, from W3 you become X1, X1 you become the Y1. Add Y1 to the round constant or rcon, which table is provided below, only for the first 8 bits. Others remains unchanged, only for the first 8 bits. Okay? For the round 1, you add 01. Round 2, you add 02, and so on. So from Y1 function, you XOR with the rcon, you become Z1 function. Okay, let's do some exercise, fun things. This is fun stuff. Okay, so key 0F1571C. So this is the key. You put in a group of 4. 1, 2, 3, 4. You put in a group of 4. So you have here 32. Each have 8. Group of 4, 8. This is in the hexadecimal. Okay. Rearrange for W0 to W3. So this is W0, the first one. (32 bits, 32 bit, 32 bit, 32 and 32. So you have word 0, word 1, word 2, and word 3. Okay, now take the word 3, okay, W3, AF, 7F, 6, 7, 9, 8. For W3, rotate 1 position to the left, okay, rotate 1 position to the left. Meaning that, okay, it's different. You don't have to convert it yet to the hexadecimal. You rotate 1 position. This is considered 1 position. This is first position. This is first. This is the first one. This is the second. This is the third, and this is the fourth. So rotate 1 position to the left. So AF will move behind. 7F will move to this one, the first, 7, 6, 7 here, and 9, 8 here. So you have here 7F, shift to the left, 6, 7, 9, 8, and AF become the last one. So this, from W3, you become the X1 function. Okay, from X1 function, bytes box to obtain sub-bytes output. Okay. Sub-byte X1 to Y1, D2, so you have D2, 85. So 7F. First, to use the sub-byte function, sub-byte box here, this is a sub-byte box. You look at this one is the row and this one is the column. First 7F. So this one is 7 and this one is F. So you have D2. So you put here first D2. 6 and 7. So 6 and 7. You have 85. And then you have 9, 8. 9 and 8 is 46. 9 and 8 is 46. Then this one is row. This is called 7 and 9. 7 and 9. B6. So A and F, sorry, A and F. This one is A and this one is 79. So this, the first is a row and this is the column. Row, column, row, column, row and column. So this is the row, this is the column. So you get the new function from x1, you get y1, d2854679. And then you add with a round constant where 3 rightmost bytes are 0. So round constant, again, this is the round constant, 0, 1.
Doctor,
Yes.
can you go back to the previous slide? Yeah. Regarding this sub-byte box, is it a default box or how it's getting formulated?
This, okay, sub-byte box.
Yes.
You have a mathematical function in order to generate this box. Okay? But you just like the S box, you just apply, you just concern how to apply the box using the row and column.
Okay.
Of
So,
course,
so
they
you
have
are
a
going to
mathematical.
give us the box. We just need to
Yes,
pick the right
given the box.
value.
Yes.
Okay. Okay.
Of course, you want to you can use a mathematical function as well, but we're not going through that. This is not a pure cryptography. This is a network security. So I just add some. If a network security is just like a process, not really fun. So cryptography, I add the cryptography part so it become more fun to learn. Okay, hopefully.
By the
So,
way,
huh? So
uh,
you don't have to memorize this as long as you know to use this in every, like if you use your programming language or you try to build up a system security, all this is a built-in already. Okay, this is not a
Okay.
new
Okay.
technology. This is the fundamental. People always skip this cryptography, they just want to use. For this one you learn the fundamental. Okay, how does
Okay.
DES, even DES is a weak cryptography technique, so they invent AES. And then you also have asymmetric where you have to know the number theory, a little bit of mathematical. That is the most mathematical that you will use in this course. Okay, we'll continue with the AES. So add with round constant where the rightmost bytes are 0. So round constant. So 0, 1, 0, 2, and so on. Round constant. Round constant is 0, 1, 0, 0, 0, 0, and 0, 0. So Z1, here you have Z1 is Y1 plus the round constant 1. Okay, we look key. This is the original key. And then you have the Archon 1010, and you have a Y1 is D285. So you have, this is a you XOR. This is a XOR. Uh, so XOR truth table, if the same function, it will return false. If a different, it will return true, sorry, or 0. If it's the same input, A and B is the same input, it will return false or it will return 0. Different input, it will return true or 1. Same input, it will return false. So this is the truth table of XOR. So you try to 0, 1, D2, you have to convert into this 0, 1 plus D2. Of course, you can use a calculator if they have. You convert to the binary. 0, 1 is 0, 1 is 0, 0, 0. This one is 0 and this is 1. And this is D and this is 2. So you convert, you XOR. So 1, 0, return 1. 1, 0, return 1. 0, 1, return 1. 0, 0, same input, return 0. 0, 0, 0. 0, 1 will come, return 1. 0, 0, return 0. 0, 1, return 1. 0, 1, return 1. So remember, XOR truth table, if the inputs are the same, it will return 0. If both inputs are different, it will return 1. So this is the XOR output. So you have 1101, which is D in hexadecimal and 3 in D and 3 hexadecimal. So the new Z1 will become D3, D3 854679. These three characters remain unchanged, only the first one, D3. Basically, if you add 0, 1, meaning you add 1, so D2 become D3. Easy. So Z1 is D3, 8546 and 79. So this W0 and W3 and this rotation word, this example, this is the auxiliary function. This is what we have discussed. 7F, 6, 7, 9, 8, AF and X1 become X1. And then you substitute using a substitution word, a substitution box, you have Y1. You add the round constant of 0, 1, you have a function of Z1. This is for round 1. Sorry, this is for round 0. Pre-round calculation. See, this is a pre-round, not even round 1 yet. So this is the round 1 for x equal to 4. W4 is equal to W1 minus 1, 4 minus 1, 3. Sorry. For x equal to 4, Wx. W0, y, I is equal to 1. 1 minus 1, 0, W0 plus z, I, Z1. For x, 5, 6, 7, Wx is equal to x5 minus 1, 4, W4 equal to 1, x minus 4. 5 minus 4 is 1. 6, 2, and 7, 3. So for round 1, the expansion key calculation will look like this. W4, W5, W6, W7. And this, we will do all these sub bytes, add round constant, mix column, and everything. So you W4, W0 plus Z1. W4 is W0 plus Z1. The Z1 we get from the add round constant. Y1 you add with the round constant, you got a Z1. So when you add, you convert back to the binary DC9037 and B0. Okay. So this is a complete calculation. DC9037, B0, and W5 and W6 and W7. So we take W7, do the process as in slide 64, the sub bytes, substitution bytes. Okay, do the process as usual. For W7, rotate first, you rotate one position. W7, you rotate one position. What is W7? 388115A7. So 81 will become the first one. 15 become the second one. A7 become the third one, and 38 will become the last one. So this is the X2. You rotate one position. Then you use a substitution bytes. 8 and 1, where is 8 and 1? 0C. 1 and 5, 1 and 5 is 5, 9. And 5C and A7, you look at here, A, and here is a 7. 5C and 07, 07. Sorry, 38, 38. 07. So you have y2, and then you add round constant 02, y2 plus round constant 2. So 02 you have to convert to binary. Okay, this one because at 0, this one remains unchanged. The three the what we call that, this one 32 bits, the 24 bits, the later 24 bits, you just left it unchanged. For the first 8 bits, you have to calculate, you have to add with the 02. You have to XOR. And the XOR will give a 0E. So Z2 becomes 0E595307. Do the same with the rest of the key from round 2 to 10. This is for the key. Okay? We are talking about the key, not yet the plain text. Again, must differentiate between the plain text and the key. Okay? All these things we use we are trying to, the algorithm is applied to the key, 1 to 8 bits key. So key, you do the same with the rest, the key from round 2 to 10. And remember the round function here, the round constant for round 1, 01, round 2, 02, and so on. For 3, 04, 4, 08, 5, 10, and so on. Now we go to the plain text. Plain text and round key. For round 0, we do add the round key. We do the add round key. Plain text XOR with key in round 0. So this is a plain text. You convert it to the matrix. Again, 01, convert to matrix, convert to matrix, and convert to matrix. Sorry. So this is a plain text, and this is the key, 0F1571C9. So this is the original key. This is the original key, 0F until 98, the original key. Okay. So this one, do a matrix addition, matrix addition by you XOR it. So 01 will add with 0F, 89 will with 47, and so on. Then you convert hexadecimal to binary and do the XOR operation in binary. Okay, you do the XOR operation in binary. So 01, so it's become very lengthy. So this is the output of it, 0E till 88. This is a plain text for round 0. And then the order of AES for plain text and round key, subbytes, shift rows, mix columns, and add round key. We will look on subbytes first, refer to subbyte box. Add output from add round key from round 0. So this output, you apply to subbytes here, subbytes. 0E, 0 and E is AB. So this is AB, 0 and E is AB. Remember, row and column, CE. This is a C, and this is the E, 8B. CE is 8B, and so on. Just check the row and column. This is after the subbytes. Yeah. And then you have, okay, the first one is subbytes done, and you have a shift row. So row number 1, no change. Row number 2, shift 1 to the left. Okay, shift 1 to the left. So this one, AB, 8B, 8935. So row number 1, unchanged. Row number 2, shift 1. So 05 will become the last 8 bits. And then 407F and 15 will become the first 24 bits. Row 3, shift 2 to the left. So F0 will become the first one. F0, shift 2 to the left. F0 will become the first one. FC 18 and 3F. Row number 4, shift 3 to the left. 2F will become number 1. Shift 3 to the left. 1, 2, sorry. C4 will become the number 1. C4. C4, shift 3, 1, 2, 3. C4 will become number 1. And E4 number 2. 4E number 2, and 2F is the last one. So this is the shift rows operation. Done. Subbytes done, shift row done. Then okay, you go to the mixed column. Mixed column, you use mixed column operation is the most extensive calculation in AES operations. If you want to look at the mathematical operation, you follow the finite Gauss field, or Gauss field 2 to the power of 2 to the power of 8, no, x to the power of 8. The mathematical details are beyond the scope of this subject, but the final formulation is important to do the mathematical operation of mixed column. So you base on the Gauss field or GF. So this one is X. You do this. This is actually a matrix multiplication. But in cryptography, use a finite Gauss field. So like X times the function of X. If the bit number 7 or the last bit is 0, this is the output. If the last bit is 1, this is the output. Where X equal to 2 or 0, 2 in hex. So you always 0, 2 in hex and 0, 0, 0, 0, 1, 0 in binary. So 2 x is 2 or 0, 0, 2. So before we start, several rules that are important for this operation. Anything that multiplied with 0, 1 hex or 0, 0, 0, 1 binary will return the same value. 0, 1 times 0, 1 multiplied with DC, the output will be DC. Okay. 03 fx, where fx is a hex representation of plain text, can be written as 03. Okay, let's say you have a 03 times fx. 03 fx, you can use 02 times XOR with 01 times fx. Okay, because 01 times fx is the same, so you XOR with fx. We'll return fx is multiplied with 01. So 03 you can convert to 02 times fx, XOR with 01 times fx. We'll return fx in, so this part will return the same fx since it multiply with 01. Just imagine it will multiply with 1. Anything that you times with 1 will return the same value. So example 03 times DC, you have here 02 times DC, XOR with 01 times DC, and you have 0 times DC, XOR with the DC. So we will begin operation with mixed column matrix. So this is the standard mixed column matrix. This constant value is used in every round. Okay, mixed column. Remember the mixed column from round 1 until round 9. The final round will remove the mixed column. So this is the mixed column matrix. You will always multiply with this one. So recall from this one, you're using a shift row, and then row shift row. Okay, this is the final shift row, AB to F, AB until 2F. So this, the output of shift row, we will multiply with this mixed column matrix. So the mixed column, you multiply after shift rows. You do the multiplication, the matrix multiplication method. Row and mixed column matrix times the column of the plain text. So like matrix multiplication is 02 times AB plus 02 times 40, 02 times F0, and 02.C4 for the 0, position. This is 01, 01, 00, 00, 01. Wait. Yeah, 0001, 0001, 00. So this 01, 02, and 03. This is 00. This is 10, 11, 11, and so on. This is a position 02 times AB, XOR with 03 times 40, XOR with 40 times 01 times with 01 times C4. 02 AB, sorry, 02 AB plus 0140, 01 F0, and 03 C4. Is it correct? 0 times AB, 03 times, oh, this one times this row times with this columns and so on. This is a matrix multiplication, the multiplication method. So you do the calculation. Okay, we'll do the first row and first column multiplication operation marked with red font in previous slide. So we will do this operation. Okay. Row 1, column 1, S00, 02 times AB, 03 times 4, XOR with 01 times 4, F0, XOR with 01 times C4. Okay, the first one, take the 02 times AB. So you use the Galois field, okay, 02 times AB. Concentrate on AB, which is in hexadecimal. Next step is to convert to binary. So AB is 1010, So bit 7 here, this consider from 0 to 7, the bit 7 here. Bit 7 is 1. If 1, you use this. If B7 1, you use this one. So you remove 1 from here and then you put here 1. So you have here before the XOR output. So based on equation where B71 at 0 at the end. At 0 at the end. Okay. From the game, since B7 we have to XOR our operation with 0010. So from this 01010110, you XOR with 00011011. 1011 0101 0100. You see here, you remove the B7, the bit number 7, and you add 0 at the end. So this is the final output. This final output, you XOR with this 0001 1011. So when you XOR with this binary, you have 02 times AB. Okay, 02 times AB. This is the final 01001101. So next is 03 times 40. We can write 02. So if 3, you can write 02, 02 and 02 times 40, XOR with 01 times 40, or the final one is 03 times 40 plus 40. Since 40 is you multiply with 01, you return the same value. So this one 0240, you concentrate on 40. B7 is 0. Since B7 is 0, we can just remove B7 and add 0 at the end. Okay, based on the Galois field. If B7 is 0, you just remove B7 and you add 0 at the end of bit. So B6, B5, B4 till B0 and 0. So 02 times 40 is you remove 0 is added at the end. So final output with 1000 and 0000. If not yet finished, we have to XOR with 40. Remember, we only finished at the first part 0240. So if 100 and you XOR with 40 hex, you have this is the final output 1100 to 0000. So many 1100. Okay, never mind. Just you don't have to memorize these techniques. We'll show, but try to understand how difficult it is to make in order to make your plain text or your data encrypted so that people cannot hack it. Okay. So back to you number 3 and number 4. When multiplied with 1, return the same values. 01 times F0 will be F0. And 01 times C4 will be C4. So you have here 02 times AB, this is the output. 03 times 40 is this the output. So you have to XOR all this. This one XOR with this one, XOR with this one, XOR with this one. So to do the XOR operation for more than 2 inputs, the rules are if all zeros or ones, output is 0. If 2 zeros and 2 ones, output is 0. If single one or 3 ones, output is 1. So this is the single one, so output is 1. This is all zeros, output is zeros. This is 2 zeros and 2 ones, output is 0 as well. This is single one, output is 1. 1, 1. This is all ones, output 0. This is 3 ones, output is 1. So you have B and 9. So this for calculation for this part 0, 0. All this one, same process you have to apply. You have to do the matrix multiplication. So this is the final output of the mixed column process, where we only calculated only for B9. Okay. This part, we only calculated for this part, B9. Position 0, 0. Others, same techniques, okay? Others, same techniques. If you want, let's say just a one like couple of words, I like to eat ice cream. And then if like the whole data or like very lengthy, like 100 pages, 100 pages of words, thousands, more than 20-30,000 words, you try to apply AES, which is your data or your file become very secure and very difficult to hack, unless of course you give the key to the hackers. It's not finished yet. After the mixed column, you have to plain text and round key, add round key. So add round key, similar process to round 0 and round key. So W4, so actual align with the state matrix. So DC, you XOR with the mixed column for final output. B9, this one is after the mixed column. And this DC, you XOR with B9. Final output of round 1 goes to round 2 input. Okay. Final output of round 1, you goes to round 2 input. Okay. This is the round key 0 you add with the mixed column output. So you have here. So this is the output of round 2 and will become input for this is the output for round 1 and it will become input for round 2. So there is it for AES algorithms. So it was designed after DS. They looked the weakness in DS. They applied triple DS, but it's a sluggish and slow. And then some of the attacks successfully penetrate the DS. So they create AES. So brute force attack on AES definitely more secure on DS due to larger size key. Statistical attacks, or you have a books of possible key. You have a possible key. Number of attacks have failed to do statistical analysis of the cipher text. Differential and linear attack is also a kind of a statistic. Like differential is like different cipher text or library attacks. There are no different linear attack and AES yet. Okay, that successful attacks on the AES. So AES advantage, it can be implemented in a software, hardware, and firmware. So the implementation can use table lookup process or routines that use a well-defined algebraic structure. The algorithm used in AES are so simple that they can be using cheap processors and a minimum amount of memory. But of course, because of you have in CPU, you have a arithmetic logic unit. So all these ALU, you use arithmetic, you use the XOR operation. So this is the comparison for DS 10 to the power of 13 decryption take about 1 hour for DS. Okay. Number to retrieve to get the key. For AES, it's almost impossible. And larger key AES is like really long years. Okay. Unless you have a very powerful and quantum computer or supercomputer that able to, I don't know, jillion decryption per second, something like that.